sit on my lap when
Oh. That's adorable and annoying all at the same time. Okay, so when we look at hybridization, right, we can combine one s and one p orbital to make two sp orbitals, right? Oops, sorry. Beep. We can combine one s orbital and two p orbitals for three sp2 orbitals, which gives us two p orbitals left over here and two p orbitals, I'm sorry, one p orbital, oh my god, over here, right? So these leftover p orbitals are going to be available for pi bonding, right? So anything that has direct bond overlap is a sigma bond. Anything that has parallel free p orbitals is pi bonding, right?
Yeah, I don't know what that means.
So that's chapter 9.1. You got work to do on that.
Sorry, I don't understand why 1s plus 1p is 2sp.
So we have one s orbital and one p orbital combined to make two sp orbitals, right? We have one s orbital and two p orbitals combined make three sp2 orbitals, right? In this case, we've used one p orbital in our hybrid orbitals. So we have two p orbitals left over for pi bonding. Does that make sense, guys?
I'll be honest, I thought I understood this before, and then when you started saying this, now I think I don't understand it all.
Okay.
I don't understand what in the parentheses.
So these are the leftover or unhybridized p orbitals.
How can you find it?
I'm sorry. If you want to, if you're having trouble with sound, you can always type to me. Yeah. How do you find what? The leftovers, right? So what we're literally saying here, maybe it will help if I do pictures, right? Is that I have one s orbital and one p orbital, right? Those are being combined to make two sp orbitals, right? Picking up what I'm laying down?
How can the 1s, if there's only one s, then how does it have that little ball on both of them?
Basically what we're doing when we hybridize is we're mashing these guys together, right? So that they have a little bit of p quality and a little bit of s quality,
Okay.
right? Now the shapes are a lot cuter in the PowerPoint because they're actually animated and nice. But the basic idea is if we took an s orbital, which is roughly spherical, and we took a p orbital, which has this barbell shape, right? And we kind of averaged them out, right? That we could get two orbitals that can increase the overlap in the sigma bond, right? So these would be sigma bonding orbitals, right?
And you have two orbitals on the right side of your equal sign because you started with 1 and 1, and
Yes.
then they just end up being a little bit of each.
Yes. So if you have two orbitals in, you will get two orbitals out.
Okay.
Right? So you can't make more orbitals than you hybridized. Does that make sense?
Or less, right?
Or less, exactly. Yes. Yep. Mm-hmm.
Okay. Could you draw a picture of the pi bond one too?
Yeah, absolutely. So just looking at this example, right? How many p orbitals do we have left over that we didn't hybridize?
None.
So an s orbital looks like this, right? But how many suborbitals are there in the p orbital?
Two.
Right?
Okay.
You with me?
Yeah.
Cool. So we have 3 p orbitals, right? Now, I drew this one like it's a pz, but really it's probably more like a px, right? Here, I'll make it prettier. There you go. So we'll say we're using the px in this hybridization, right? So we used this guy, and we used this guy to make our hybridized orbitals, right?
Yeah. So the PZ and your PY are your leftovers? Or?
That's right.
So then you have 2 leftover orbitals?
Uh-huh.
So basically whatever ones you don't use.
Mm-hmm. Right? So, if you have a single bond,
Professor, I think you have a question in the chat.
thank you. Honestly, it doesn't matter. I'm just talking about the px orbital because if you're looking at a bond along the x-axis, right? So just thinking about 2 atoms, right, that are sitting next to each other, right? So when you're talking about an sp bond, what geometry is that?
Linear.
Linear, exactly, right? So sp is linear, right? So these guys are sitting right next to each other. So you know it's linear. So the most probable one to use will be the px, right? But technically speaking, the x, the p, and the the x, the z, and the y are all a matter of orientation, right? In 3 dimensions, so it's kind of arbitrary, right? We just happen to orient our bonding molecules along the x-axis, right? right? But they could be this way. It could be, right, straight up and down. Does that kind of make sense?
What does that say?
Oh, what?
Sorry, what does that say in the parentheses?
Unhybridized.
Unhybrid. Okay, unhybridized.
Yeah.
Okay.
So a single bond is always a sigma bond. Okay? Sigma bonds have direct orbital overlap. Right? Do you guys know what I mean by orbital overlap?
No.
Like sharing of a bond.
Yeah, so remember we said that covalent bonds share electrons, right?
Yeah.
And the way that they're able to share those electrons is by taking imagine my s orbitals are a little bit bigger, right? Well, let's say this is atom 1 and this is atom 2, right? This section here is direct orbital overlap. Does that make sense?
Mm-hmm.
So this is a sigma bond. Coolsies?
So would
My
the
sigma
bond
symbol is not
between,
great,
like
but
a carbon and a hydrogen be a sigma bond?
yes. Mm-hmm. All single bonds. Whoops. Single bonds are sigma bonds. Okay. So direct orbital overlap is what's required for you to have a sigma bond. All single bonds are sigma bonds.
So for a double bond, would it be one single and one pi then?
That's exactly true. So a double bond has one sigma bond and one pi bond, right? And the sigma bond, as always, is going to be this direct orbital overlap, right? The pi bonds result from having two atoms next to each other that each have a free parallel p orbital, right?
What's the A mean?
It's atoms. Atom 1, atom 2. I'm purposefully ignoring the sigma bonds here, right? Because it would just make this picture way too crazy, right? But they're there. You guys cool with me on that? So what you get in a pi bond is not direct orbital overlap, right? Instead, what you get is these p orbitals that electrons are able to hop between, right? So this allows for electron delocalization, right?
Yeah, this is just like a bunch of stuff I never went over, so.
Yeah. It's really hard to learn this stuff on your own. I mean, we talked about it in the lecture, but it's a really challenging subject for sure. So the one other thing that I want to point out to you about the pi bonds is the way that I've drawn these p orbitals is very static, meaning they're not changing, right? But you can imagine that these orbital shapes are dynamic, right? Whenever atom 1 comes into contact with atom 2, right, it's going to change the shapes of these orbitals, right, based on repulsion and attraction interactions. Does that make sense, guys? So what really ends up happening with a pi bond is we're not jumping these great vast distances. What we're doing is we're kind of making an elongated p orbital between atom A and the other atom, right? Does that kind of make sense? So we have this area right here, which is a node, right? That's where the electrons don't want to hang out. And we have these little areas of electron density. And what we're saying is basically when you have these two atoms able to interact with each other, the p orbitals kind of spread out to get closer to each other. Sorry, it's not a cute picture. But that's basically what you have. You also have, with a sigma bond, these are longer, okay? So sigma bond is going to be longer. Every time you add on another pi bond, the distance between these, r, gets smaller. With every pi bond you add. Does that make sense? So basically, by having these parallel p orbitals, right, that makes the atoms come closer together in their bonding, which increases the sigma overlap, right? But also gives rise to this delocalization that happens in the p orbitals, right?
So in this pi bond, there is a sigma bond happening at the same time simultaneously?
Yes, absolutely. You can't have a pi bond without a sigma bond, right?
Okay.
You can have a sigma bond without a pi bond, but you can't have a pi bond without a sigma bond.
Right. Okay, I got it.
Okay? So that was a double bond, right? Now if we look at a triple bond, that's going to be one sigma bond still, right? We always start off with a sigma bond and two pi bonds, right? So in order to do two pi bonds, you need two free p orbitals on each atom. Okay, so before we were just starting off with our 2p, right? This gave us one pi bond, right? But now we're saying we also have another, I'm sorry, my three-dimensional pictures are very bad, right? These other, so let's say this was PZ and PZ, right? Maybe this is PY and PY, right? I'm not drawing them on top of each other because it gets really ugly really fast. But can you guys picture that these are superimposed on top of each other?
Yeah. I was actually just about to ask you that.
Yeah. Sorry, if I draw them together, it just gets really ugly. So, and I'll show you guys a pretty picture in just a second, okay? I just want to get through the basics of what we're talking about here, right? So this gives you your first pi bond, and this will give you your other pi bond, right? So having this pi bond is going to make R smaller, right? R being the distance between atoms in a bond, right? This one is going to make R even smaller. Right? So, when we talk about bond length, right, which is essentially your R, the shortest bond is a triple bond, right? Then you've got a double bond, and then you've got the longest bond is a single or a sigma bond. Right? How are we doing with this, guys? Is this helpful?
Yeah, this was really cool.
Good. I'm so glad.
I didn't even realize that I didn't know this.
Yeah, if you've gone through and read the chapter in great detail, you know, you might have been able to pick this up, but it's kind of a difficult thing to learn without being explained. So, yeah, I would say hybridization and some of the quantum number stuff is the thing that students struggle with the most in chemistry in general. So I would say, honestly, guys, if I had to pick a hardest test, I really think it's this one. And I'm not trying to intimidate you at all. I'm just trying to let you guys know that if you make it over this hump, then you're sitting pretty, okay? Not saying, you know, rest on your laurels or anything, but, you know, relatively speaking, I think the first test is the easiest, the second test is the hardest, and then the third test is somewhere in between, right? Cool. So bond length has to do with basically how many sigma bonds, pi bonds, or 2 pi bonds you have, right? And the bond length is proportional to the bond strength. So the shorter the bond, the stronger.
It was inversely proportional. So
Did I'm sorry, yes, inversely proportional. Bond. Oops, no. That's going on the internet forever. Bond strength.
Thank you for just making that.
I do what I can. Bond strength is inversely proportional to bond length. That was a good one. Right? So the longest bond would be the weakest, and the shortest bond would be the strongest. Okay. Let's see. Alright, so I'm going to do something really weird here, but I'm going to show you guys the pictures of what I'm talking about here. So these are the cutie pie pictures, right?
Yeah, that helps.
Yeah. And again, if you go through this area of the PowerPoint, there's lots of really pretty pictures, right? It shows you how all of these orbitals are being combined, right? To make these new shapes. And then to your, right, so this is the one that I didn't draw because it's absolutely horrible to look at, right? But when you have two pi bonds, right, you've got the sigma bonds here, right? And then these free p orbitals are the ones that are doing the first pi bond, and then this free p orbital on the carbon, and this free p orbital on the other oxygen, right?
So, like, in that situation, do you have any leftover bonds? Or leftover,
So all of your p orbitals there are being used. One of them is being used in sigma bonding, and two of them on carbon are being used for pi bonding, right?
Okay. So there's no leftover orbitals.
That's correct.
Okay.
Well, technically, yeah. So then the question that you were asking originally is, where do we get the d orbitals that we use for hybridization? So the first d orbital that we use is this dz squared, right? Which has an axial component that can be used to hybridize in the sp3d, right? And the second one has the dz squared, but it also has this guy, which is the dx squared minus y squared, which also has axial components, right? Which is able to help you get this sp3d squared shape, right? So the answer to your question of why these particular d orbitals are involved in hybridization is because they have axial components. Okay, let me see if I have any pictures of my orbitals by themselves. Let's do. So, okay, so here we get into the d orbitals, right? Do you see how these three orbitals are all out of the axes? Meaning they don't have axial components. They don't lie directly along the axis.
Except for that last one, right?
These two have axial components, right?
Okay.
Those axial components are what allow it to help with sigma bonding, right? Again, sigma bonding is happening along those axial components, right? So that's what's helping you when you're mixing in those d orbitals, okay? It's not super important to know, right? But it is important to know that the reason why these aren't involved in hybridization is because they don't have axial components.
Okay. And then how would you, like, for the answer for that question, how do you then know if it's the second to last one versus the last one?
I wouldn't ask you something that specific. Basically, I just want you to know that these guys are both axial, so they can be involved in hybridization.
So, because I thought that last one, I can't read it that well, but it says dx squared, right?
Yeah.
I thought that was, or dz squared, that wasn't one of the options on the quiz?
It was.
Okay, well, that's what I'm asking, like, how do I know that the correct answer was dx squared minus y squared and not dz squared?
It was both.
Oh, okay.
Yeah. It was
Oh,
both.
it was minus.
So it was
the
question was explicitly asking which d orbitals or d suborbitals are involved in hybridization. Right? So it wasn't asking about the specific sp3d or sp3d2, right? It was just asking which ones are capable of hybridizing.
So there were 2 right answers.
No, there was one answer that had both of those.
Okay, I gotta look at this one.
Yeah. Yeah, go ahead, Maya. So, just real quickly, anybody else have more questions about hybridization, or can I turn my video recorder off?
Okay, I see.
Which lecture? That's chapter 7. I don't have it on my canvas. That PowerPoint.
So the chapter 7 lecture we went over last Thursday.
Oh, I'm sorry. Which chapter? Oh, okay. I was looking at the chapter.
I know, it's a lot, and it's super hard to keep all this organized, too. So the chapter 7 goes into orbital shapes, why they exist, and the quantum numbers that allow them to arise, right? Where chapter 8 is getting into how those orbitals are being used in hybridization to accommodate Vesper theory, right? Now remember, Vesper theory is saying that all of the electron groups in a molecule want to be as far away from each other as possible. So the molecule shape, the molecular shape, will always form the shape that gives you the maximum distance between electron groups, thereby minimizing the overall energy of the molecule, right? So the way that we accomplish this is by doing this hybridization process. And the last slide here, I'm pretty sure that this video is Crash Course, which has some really nice animations showing like how the orbitals mix together, which I think is kind of cool.
What's the name of the Crash Course video?
This whole PowerPoint is on Canvas.
Okay.
So.
Is that the 8B or?
This is 8 and 9.
8, 9.
Mm-hmm.
Really quick, the quantum numbers